So unless there are other questions, let's talk about Goppa codes. Let's start talking about Goppa codes. I promised you that it's going to be now. So it's actually quite straightforward from what we did. Any other questions? Okay, yay, Goppa codes. So this is a rare time in the lecture where the word code appears at all. You will see it now, and you will see it in lecture 12, and you'll see it in the recitations also. Good. So I want to show you how we define codes from function fields now. And but I do need one definition, one minor definition. So let's write it before. So let's say that f over k is a function field. So we have a function field and a prime divisor p of degree 1 is called rational. It's called rational. Okay, so just a name, right? Every prime divisor has a degree, right? If you remember, the degree of a prime divisor is the index of is this thing. It's, you look at the residue field, which let's denote by f sub p from here on. I think we used it once maybe. So this, right, this extends this field. It could be k, it could be a extension of degree 2 or whatever, I don't know. And if this is k, or technically like isomorphic to k, then we say that p is rational if the degree is 1. If these two are the same. Okay, it's called rational because like you walk over k and you ask for prime divisors are points, right? So a point in number theoretic language is rational if it's like in the ground field that you are walking over. And in our case, this corresponds to this f of p. So this thing being k is like a kind of a special case. It tells you that when you're going to evaluate at the point p, you're going to get thing from k and not from an extension of k. Right. Like in number theory, so that's like from Q or something. So you walk over Q and you don't, like if you solve a quadratic, if you have a curve over Q, then so rational in the sense of Q, then you may have some solutions or maybe in the complex plane, in the complex field, but not rational solutions. You want like fraction, you want rational solutions there. So I think that notion got stuck. I don't know where I saw rational. It's just a word for us. Okay. So right, so this means that just to make sure that we understand, this means that the evaluation map sends a function. Usually I should write here this thing, but I'm going to write k now. Union infinity, of course, because I don't know. Right, usually what you write is the fp. That's where the residues are. And as a little bit of notation, right, this thing is saying like I'm evaluating f at p in the technical sense, I'm taking really what I'm doing here is doing like something like f plus mp, right? Technically speaking, like algebraically. But really what you think of is I evaluate f at p. So we are going to denote it like that just for the purpose of this Goppa code description. Okay, which is more like kind of give the emphasis on f and not on p in a sense. And it looks like an evaluation. But what really happens is this thing. And if the place is rational, you can actually think of this as k. Like not this. Yeah, you can think. Right, exactly. So you can think of this as k. So you can think of this as an answer in k. That's what I wanted to write. I can think of it as an answer in k. Right? Good. So let's write the definition of a Goppa code. And then after the break, we are going to analyze it. So maybe I need a bit more room. And yeah, so you can. Yeah, but we are not going to use it after this. We'll only use it in the context of codes, really. It's not really used for. I mean, I think Stirnov does use it, but like this notation, right? But P is fixed. P is like the evaluation map. It's like the place corresponding to P. We defined it. I mean, given P, we defined it. So let f over k be a function field. And P1 up to Pn rational. So I'm not taking just prime divisor, I'm taking rational prime divisors in this sense. And so these are the ingredients for the code. I need n rational places or rational prime divisors in my function field, and I need another divisor, any divisor that you want, but I don't want these to appear in here in the divisor. So I wanted the support, right? A is like a bunch of like 5 times this p times minus 6 of that. I don't want this to appear there. So one way of writing that it's like over formal, but right. So if I extract the pi coefficient of A, I get 0. And then I can define the code. So define C. So this is C of the function field, and with respect to this rational places, this divisor, but I'm just writing C. C is just this subspace. Right. So what are you doing? So you use A, the divisor A. So the functions that you are going to evaluate are coming from the Riemann workspace corresponding to A. So for every function in this Riemann workspace, you're going to have a code word. So you should think of this as the messages, if you will. And then what is the code word? So what you're going to do is, the ith location, you're going to evaluate f at pi. And that's it. Like that's what you do. It's very similar to Reed-Solomon, right? I mean, Reed-Solomon, this thing is k of x over x over k. You take only polynomials, but if you want to put it in this framework, when you say I'm working over the rational function field, I'm only taking polynomials, but over the rational function field, these points are just elements in the field. So these are just, we call them like alpha 1, alpha n in k, in like F5 or whatever the field is we're working over. And what is A? No. Zero divisor are 0 dimension, like dimension 1. Only constants. So what are you evaluating at read zone? Exactly. Yeah. So you're evaluating all polynomials of the degree at most R. So A is this R times P infinity. And then that's exactly what you do, right? You take your functions here, which is a polynomial. I mean, it doesn't have to be a polynomial. It's a polynomial because it shows it like that. So these are polynomials of degree at most R. And you're going to apply each of them to a different point. And the fact that these points are in K and not in like a field extension of K is exactly saying rational. So you wouldn't even dream of doing that. Okay? You won't take F5 and then you're going to evaluate at something in F20, like F25, and consider it as something, two things in F5 or something. So that's what you will immediately do. So this is why it's an extension of Reed-Solomon. Right. So So here, the way you analyze it, so we'll do it now, and then we'll see how it generalizes Reed-Solomon. But the rate is determined by how many elements you have here, and the distance is determined by the by the easy part of the fundamental theorem of algebra. Like every polynomial has at most that many zeros. You don't have to have exact for the analysis, only at most. And we are going to use the same thing essentially. So after the break, we are going to analyze it, but with the more general setting, in the more general setting. Okay, so let's have a break. Right, so maybe before we continue, because I got some questions during the break, let me just kind of, just as aside from the Goppa code, let me just again remind you how we think of everything here, like what are valuations and points and rational points and evaluations and so forth in the picture, but without proving anything, because technically I can't prove it, and that will take a lot of time. So there is this picture here. So yeah, maybe I'll just use this. So how does a function thing look like? Looks like, it looks like, a transcendental degree 1 extension, blah, blah, blah. But how does it look like really? Like how do we are going to use it? So it is, sometimes you can write it as, you take a field, maybe this is F5, just for fun. And you adjoin to it two transcendental elements and require an algebraic relation between them. That kind of intuitively gives you a transcendence degree 1 here. It's not clear that the field of constant is F5, but just ignore those things. In this case, it's fine. And so this is a function field. That's how it looks like. All x and y's, all these functions, x squared over y plus 1 and so forth. But you always live under this algebraic constraint that y squared is x cubed minus x. So every time you see a y squared, you can replace it, and you just scan. You have to replace it in a sense by x cubed minus x. That's the algebraic relations I was talking about. So, for example, if you allow me a y and an x cube and an x, then like in my Riemann-Roch space, I can work with those. And when you say you're also allowed to use y squared, you gave me nothing, because I can write y squared using those. So that's why you have deficiency. See, like there are algebraic relations which, if you allow me something new, it may not be new, because it can be expressible using the algebraic relations with what I already have in the Riemann-Roch space. So that's what I was referring to about algebraic relations. Now, a point is actual point, so I don't think that's a point. So a point is a point. So a point is like a pair of F5 elements, okay. So a point is any solution to this equation. Right, so when I said that, usually you think of F5, because the function field is defined over F5, so you think of F5, so maybe you substitute here 1 and here 0, and that's a point. And so this is some point here. Maybe this is 1, 0. So this is a point, and that's a rational point. A non-rational point is a point where one of the entries here is not in F5, in F25 or something. I'm not proving that you should like relate these two, but just how you think of it. A non-rational point doesn't live in the space, in the field that you can thought of. So for example, if you take x to be, what did you choose here? 2? 3? 4? I think it was 2. Yeah. So if x was 2, then you have like 8 minus 2, which is, no, so we chose another number here, I forgot the number.
Yeah, that makes sense.
Right, it made sense before. So I'm not sure if you can get a 2 here, right? See? Right. So let's say you put an x and you get a 2 here, just for fun. You should take another example, like -1 or something, and then it's fine. Do this. Then you see, this has no solutions in F5. There is no y that solves that in F5. But there is one in F20. There are actually 2 in F25. Yeah, exactly. So I'm walking over F5, and I get this equation, which has no solution in F5, but it has solutions in F25, because it's a degree 2 extension. It's standard Galois thing. There is a solution in F25. 2 solutions, and they're actually conjugate. The difference is the minimal polynomial. These two are conjugates modulo F5. And these together constitute a prime divisor of degree 2, because these two are 2 points, like together, or 2 points in F25.
Right? Each one of them is the same prime divisor, right?
Yeah, right. So we take the prime divisor really to be, in a sense, their sum. Yes. And what will happen is that this will be F25 and this will be F5. So the index here is 2. And when I say, so like geometrically, when I say rational points, I mean points in which these two coordinates, and by the way, generally it doesn't have to be two coordinates, it can be many coordinates, but all the coordinates are in the ground field that we care about. The K, F5. And okay, so that's point. These are points. Rational points are actual points on the curve, like with entries from the ground field. A function is like, functions like, whatever. You have x and y, take a function, like maybe 1 over x minus 2. That's a function. It's defined here, right? I think you can plug 1, you don't get problems. It gives you -1. So this means that this function is in O of this P, but by the way, not in M of this P, because it's not 0 there. If you'll do like a y over x minus 2, that's 0 here, right? Because the 0 here is. So that's in M of this P. Well, and good. And so when you evaluate at a rational point, you always get like an element from F5 from the base field. If you're going to evaluate whatever that means in an element from F25, you can't really evaluate. It's like 2 points. How can you evaluate? So what you do is you divide by their minimal polynomial, the joint minimal polynomial. So you get a polynomial of the greatmost 1 now. It's not an answer from F5, it's an answer from F25. Okay, hopefully this was helpful. And in this situation, what happens, right, is like you choose your points, so you should think of them as points on the curve, right? And then join the points like in a plane, but a curve doesn't have to live in a plane. Okay, it can be like this, I don't know. And in our case, it will be actually. So you have points on the curve, but you take points on the curve, like points with all entries sitting in the ground field. These are rational points. Like in our abstract algebraic notation, I never said that, but that's the correspondence with geometry. And you take a divisor. A divisor is like, right? So there is this point at infinity. So I'm not sure where to put it. Like maybe here. Right, actually, yeah. So in this example, there may be several points at infinity, but it's not like there is a point at infinity. The rational function field, there is a point at infinity. In a general function field, there can be like a line at infinity in a sense and so on. But you take a point at infinity. So here I just call it A. There is no infinity, like kind of intuition attached to it. And but that divisor could be anything, right? It could be like a bunch of points, and you say I want functions have at least 5 zeros here, and it can allow to have 8 poles here, and so forth. That restricts the set of functions that you can have. And because, as you'll see in the analysis, because A and the P's are kind of the support of A is disjoint from P's, all the functions here are well defined at these PIs. Because you have no poles there by definition of A. So what you do is you take a function and you evaluate it, like polynomials. Polynomials of the greatmost R, you can evaluate at every point in F5, but you can't evaluate at infinity, not that you ever thought of doing so, but you can't evaluate at infinity. Right, so here I'm using polynomials and not rational functions, and that, like Reed-Solomon is kind of, this is the easy way of making sure we don't get like aborts or infinities here. Okay, good. So hopefully that was helpful, but let's go back to our Goppa codes and let's analyze them. And maybe we can throw 1 or 2 more questions about places if you want to the homework, like not for submission. The second homework is like fairly long anyhow, because we wanted you to, I mean, you asked for it, you literally asked to have questions so that we can engage with the material. So yeah, we found a lot of questions that, but we only put those we can solve, which is a good filter. And yeah, so, but we can add more questions, like just for fun. So I'm going to analyze this code, but in order to do so, I'm going to consider a special case. Just for fun, you can analyze the general case, the same way, but just for simplicity, so we'll consider the special case where A is just R times P0, like in Reed-Solomon, where P0 is not one of the PIs, Right, so in particular, the support requirement here is valid. Okay, just a little bit cleaner, that's it. In R, you'll see I'm going to take it at most n. Okay. So the theorem is the following. And that's going to answer kind of Yuval's question about what do we care, in what parameters we care about the code, the curve. So C is a linear code. That it's linear is kind of obvious because it's like that. A linear code of dimension at least R, this R, minus the genus plus 1, and distance at least n minus R. Right, so you have R is a parameter. N is not a parameter. N is how many things you output. It's like the code word, the block length, the code word length. And G is a parameter of the function field, and R is a parameter to your choosing. And you can play with it, and you see as you increase it, you decrease the distance, but you increase the dimension, and the other way around. In particular, if you just add these two and divide by n, you'll get that rho plus delta. Right, rho is the dimension divided by n, right, the rate. And delta is the distance divided by n. So what you'll get, the r's will cancel, and you'll get this thing. Right, and that's, now to Yuval's question, that's exactly what we asked before. So what do you want? You want the sum of these two to be large, as close to 1 as possible. You can't beat 1. And what is written here is that if you want it to be large, then you want this fraction, forget about the minus 1. You want G over n to be small. So you want the genus to be close to the to the block length, to the number of points that you have in the code. Exactly. When G is 0, this is exactly the singleton bound, yeah, which we proved Reed-Solomon actually attained. Yeah. In Reed-Solomon, we took these to be from the field elements. So the field was required to be at least n. Here the field can be f5, and what I want, that's the whole point I forgot to say. And what I want is just many points on the curve, not on the base field, on the curve.
Get a fixed field and you still build a code.
Right. So you have a fixed field, and maybe you can get a code with many rational points on it. You want a curve with a lot of points, a lot of solutions to the equation that you have. And you're right, this is always worse in Reed-Solomon, but it's not a fair comparison because the field size is fixed, for example. Right, so, I mean, we do have to understand how a genus behaves. N is like a special number. N is a very important number. N is like, right, that's like the Diophant's kind of questions, like how many points you have on a curve. It's a very deep problem, essentially Riemann's hypothesis. And it's related to the...
You can't like enlarge n as you want. You have like n is like bounded in some sense is related to G. Right?
So you can increase n by adding more points maybe, but then G will increase. And the question how they kind of relate is extremely deep.
Like, how like...
And we're going to prove everything about that. But essentially understanding that relation, and we're going to talk about it afterwards, is like the resolution of it is solving Riemann's hypothesis over function fields. Very deep. But here it kind of nicely, the genus and the number of rational points on the curve corresponds to the distance and the rate of the code. 2 parameters in the math world gives you 2 parameters in the code world. Okay, so but let's do the analysis. We have to start proving it. So, I mean, most of it is. So first of all, C is well defined. Like C, I mean, in what sense? So first of all, C is in K to the n, right? It's a subspace in K to the n, right? Because these are rational points. All of these are coming from K, and they are all defined, right? Because the PIs and A, or our P times P0, are disjoint. So this means that every function here has no poles on the PIs. There is a 0 at the divisor location of the PIs, so you can't have a pole. Right? So let me write it more formally. So the same thing, because we choose f from the Riemann-Roch space, then we know that for every point that we have, you have a non-zero here, and like a non-negative element here. You actually have a 0 there. Okay, and so this means that, right? So this means that you have no poles. So f of pi, which is technically phi pi of f, is in K because it's rational and not infinity because it has no poles. It's obvious that it's linear, right? I mean, if you have f and g, you have f plus g there, and the evaluation is linear because this function is linear. So linear is checked. You need to check although taking a product of a scalar, but that's obvious. This code is linear because you take a linear subspace and you do a linear stuff to the element that you took. You apply linear transformation, phi of pi. So these are linear stuff. And to erase this. And the interesting part is analyzing the distance and rate. So as for the distance, where's the rate? As for the distance, so let's see. So let's take an element in the Riemann-Roch space that we are evaluating from, and a non-zero element, right? It's a linear code, so what you have to show is that if you take a non-zero message, you get a non-zero code word, but even with a lot of non-zero. Right, so I'm taking the non-zero element here. And let's assume that it has some z zeros out of these pi's. So let p1, or maybe let's call it pi1, up to piz be the zeros of f. Because this is a linear subspace, and this is a linear operation, it's applying phi. And phi is a linear, it's homomorphism. Right. But evaluating at a point. So right, f of 5 plus g of 5 is f plus g of 5. Good. So you take a function, non-zero function, and you take, let's assume that out of these p1 up to pn, and these are its zeros, z in number. So what I know is that f lives in this Riemann-Roch space, where a is rp0 minus pi1 minus piz. Right, you started with a function at rp0, so it was there, it is there. But then you know that it also has zeros, at least like with multiplicity 1, zeros at these places. And so this means that I can actually say that not only f sits in this Riemann-Roch space, but in this more challenging, smaller Riemann-Roch space. Right? Because in this Riemann-Roch space, you allow for r poles at 0, and f has r poles at 0 at most. And you require a 0 at pi1 and a 0 at piz, but f has those zeros. Right? So f, because it has many zeros, and I know them, I can kind of say, well, actually, f doesn't just live in the Riemann-Roch space of that, but of that. Good. But just recall that generally speaking, if the degree of a divisor is negative, then the dimension is 0. Right? You remember if you have more constraints than when you allow me stuff, you don't get anything. You get only the 0 subspace, 0 dimension. So just as a recall. So this means that, you know, the contrapositive of that says that because this Riemann-Roch space has a function which is non-zero, if it's non-zero, then its degree is non-negative. Right? So this means that the degree of A is non-negative. Because if it were negative, and if it was negative, then F couldn't have been there. But what is the degree of A? Exactly. R minus Z. Because it's the degree of this thing. All of these are rational places, namely degree 1. So you have R times 1 minus Z times 1. Good, so this means that Z is at most R. So the number of zeros is most R. And so the distance is at least n minus R. Okay? It's like saying really, you know, think of Reed Solomon. If this was degree at most R and it had these zeros, then like every zero like that is another linear constraint. That's what's happening here is another linear constraint. And you can't have and you can't have any zero, like maybe 5 is 0, so x minus 5 divides your polynomial. And then 3 is there, so x minus 3 divides your polynomial. It gives you linear constraints on where this polynomial can live. And you can't have more requirements than, if you have degree R, you can't have more than R roots because every one of them gives you a linear constraint. So that's really what's happening here, but abstractly. So as for the rate analysis, that's kind of essentially obvious. The distance was interesting, the rate is. So first of all, right, okay, so it's actually a little bit, the way we do the distance before is now that we know that there is a distance, I mean, the distance is at least n minus R, and I'm assuming it's, who wants a code which is not bijective, right? So I took R to be smaller than n, obviously. Then this means that the dimension of C is the dimension of LA. Right? I mean, potentially there could have been two F's, F and F prime that goes to the same code word, but then that's not a code. And we just prove it's not only it's bijective, it has distance. Right? A code is really a strong bijection. Like there is a distance, not just no collisions. So that's why we know that the dimension of C, there are no collisions, is at least, or it's equal actually, exactly, to the dimension of the Riemann-Roch space, which we just write like this all the time. A is in our case R times P infinity, but P0, sorry. So that's that, which is exactly R. Sorry. I completely failed, like all the Riemann stuff. So what can you say about this dimension? So the dimension is at least the degree minus the genus plus 1. That's what Riemann told us. He told us that the degree minus dimension can't be like too large. Yeah, because you can't, I mean, at some point, am I saying it right? Yeah. And this thing is R, so you get this R minus G plus 1. And technically, that's it.
Maybe also good genus, but particularly a nice divisor doesn't reach the maximum.
That's a great question. Potentially, this bound is like, I mean, okay, that's a bound, but maybe you can find a divisor that like has a better, you can analyze it better. So technically you can, but it's kind of restricted. So it turns out that once the degree of the divisor you care about is large enough, 2g minus 2, if you care, then we'll talk about it. Then this loss is always there. So if you want to find a divisor that kind of beats this annoying stuff, then it has to be of low degree. And now it's really kind of hard to understand what happened in low degree divisors in Riemann-Roch spaces, but in function fields. But you do. There are examples where you can take the Hermitian Riemann function field and take a divisor that goes below that, and it has a better loss because there are smaller the losses increases. So it makes sense to take a smaller divisor. It doesn't give you a good code, but it does give you a good epsilon bias set and stuff like that. It's a good idea. Don't worry about this bound. Just find the divisor that behaves better. But the bottom line is that it may help you, but it typically won't help you. Yeah, because that's the standard behavior. The typical behavior is there is a loss of G minus 1. But we're actually going right there now. So we call it like walking below the genus or twice the genus, and it's scary because you don't have tools. You're on your own. But just as a recap, so what we want to do, given this, so the question is, So say you want to construct a code over FQ for a fixed Q, right? So given Q, technically it should be a prime power because we are working in finite fields and stuff, but given Q, we would like to find a function field, well, maybe, given Q and N. So Q is 5 and N goes to infinity in my mind. So we'd like to find a function field with N rational points. So the way you should think about this is the curve has many rational points. There are many solutions in the base field to the equation y squared equals x minus x that minimizes this quantity of genus, so G over N, genus over a number of rational points. You will take all the rational points that you can. I mean, why not? And you want to minimize this because that's exactly the loss. The one minus that you have is this thing. And it's like a huge question. How, for a given Q, how good can this be? How small can this be? You want this to be 0 if you could. Q is is the field size. Yeah. So, all right, so this is what you want, right? And so it turns out, so there is some bad news. So the Hasse-Weil, there is a theorem by Hasse and for a special case, and then Weil, long history to it. The Weil bound were obtained in 1948. These were the 20s and 30s. And, there were people before that kind of tried to answer these questions, really. For function fields, they kind of defined it and tried to answer those questions. They didn't know codes. There were no codes. Actually, I think codes were defined around the same years, but I don't know. So they showed that G over N, so these are the bad news, that is this thing. Namely, you want this number to be small, but you have fixed Q, so it can't be that small. It's like 1 over square root Q, essentially. And then actually, two other, their result is stronger and it implies that. But if you care about this question, you can take their techniques and prove something stronger. And this was done by Drinfeld, because that particular ratio wasn't of interest to them. They care about something a bit different, some additive error, not multiplicative error. So if you do the right thing, if you know that you care about this and you understand completely their proof, so what you can do is that you can show that actually the bad news are even worse. Something like that. Twice as much, I don't know. Any function field. Right, so for any function field. No, for every function field this holds. No way you can get a code from function fields with else. Well, unless maybe you do something like you said. Don't use that. Take a divisor, a special divisor, and stuff like that. But it usually won't help you. I mean, it doesn't help. And then, these are bad news and bad news. But then, remarkably, there was a result that proved that this is tight. So, so this is a work I don't really understand. So it's Fassman, Vladut, and Zinc. This is when I was born. So now I feel like it's like real. This is like stories, and this is real. Proved using things I don't quite understand that there exists a function field. They didn't found it. Just proved the existence using like modular curves or something. I don't quite know what that is. That there is a function field such that G over N is at most this bound. I think you need Q to be a prime squared at least or something, but never mind. The equality is in the other direction. So what's the problem? They proved equality. They proved that for every function field you can't beat that number, and they found proved the existence of a function field that has this number. And so I don't know that. I can't teach you that. But the first explicit construction of function fields, which we'll see, was obtained by Garcia and Stichtenhoff. Stichtenhoff is the author of the book. So he really knows what he's talking about. Using towers of function fields, which you'll see, which attain this bound. And now we have many examples of function fields like that. They are not typical, but you can have many constructions. Good, and that's what we are going to, that's where we're heading. But before we're doing that, we have to do one thing, is prove Riemann-Roch. So the goal for the rest of the course is as follows. We're going to prove a strengthening of Riemann's theorem. Riemann's theorem is an inequality, which right, you wanted to maybe bypass somewhere. So Riemann-Roch theorem, Roch was a student of Riemann, and he kind of proved that theorem. And again, none of them proved those theorems. These are theorem complex over complex Riemann surfaces over the complex field, and all of these proofs that you will see are algebraic, and there's nothing to do with what happened in those papers. So the proofs are really very different. Yeah, so we'll prove this theorem. That's going to be not easy because it's extremely abstract. If you thought that OP and VP is abstract, you're going to. But then after that, we are going to kind of go downhill, and things will be more Galois and nice, I think. And if you understand what happens, but we have to prove that. If you don't prove that, you don't understand what's happening. And then afterwards, we are going to continue our development. We are going to talk about function field extensions. That's essentially the entire course, really, but the remaining of the course. And during that, we are going to prove Riemann's theorem, really. We're going to analyze the zeta function. And you may wonder, how can you do that if we are at week 7, right? And there are like 13 weeks, and it doesn't make sense. So what we are going to do is the following. So because I don't want to use slides, because then it's like literally like 1.4 or something in terms of pace. It's too fast. So what I will do is I'm going to prove, I had to prove everything so far, essentially, because these are like the basics. You won't understand the definition if you don't see the proofs. But in many of these things, there are theorems that you can like completely understand, believe, like this is a normal extension, okay? Without seeing the proof. And the proof could be 2 hours, okay? So what I will do is I will start slowly, but surely we are going to omit some of the proofs. I'm choosing them very carefully, so not to have good like balance of understanding and time. And all of the proofs I'm recording in videos, and I'm putting them on the YouTube channel. They're also in the notes if you prefer, but maybe it's a bit harder to read. So I'm going to do that anyhow. I actually started doing that. This is what I did in the past few weeks, and I'm going to omit some of the proofs, and that's how we are going to compress back a factor of 3 in pace. But Riemann-Roch we are going to prove, but for 2 little lemmas which are recorded. Okay. So questions about where we are going, what we are going to do, stuff like that.